Now coming on to the receiver part, we will open the OFDM RX file. In the receiver, we'll first need to check what signal are we receiving. Firstly, the packet detection algorithm that is being used is delay and correlate algorithm, in which the signal that we picked from here, this RX signal, that is going to be processed. But this RX signal is oversampled by 8. So the first thing that we will try is to try and give original signal for packet detection. For that, we'll try and reconstruct the original signal from this convoluted signal. In the receiver, when we see in the transmitter, the last part that was done was passing the signal through a filter. So in the receiver, firstly, the signal has been passed through a filter. After passing through the filter, we'll try to get the signal before oversampling. So for that, we'll take the original signal. And since we discussed in the transmitter, after convolution, the here when the oversampling is 8, the number of these coefficients that we have are 49. We can see this when I run the code until line 22. Okay, I didn't change the oversampling to 8. When I change the oversampling to 8, we'll see the number of coefficients that are defined are 49. Hmm. So the number of coefficients are 49. In these coefficients, the first 24 are appended before the RX that we had of 12,200 symbols, and the next 24 are appended after RX. So we'll try to pick up from the 25th sample after every oversampling factor interval. We will pick the samples until the length of this RX signal minus the last 24 symbols. So this is how we have tried to construct the original signal to give to the packet detector. Now let's see what type of signal we have, the RX signal. From there we'll know how to set these both factors. So when I check the signal that we have reconstructed, that we are going to give to packet detection algorithm, when we zoom into this signal, we can see that the periodicity of single element is 8. After 8 samples, a single element will be repeated. This peak is at 20 at 15 and it will be repeated at 23. So after every 8 symbol, we will get perfect correlation. And since we know in the transmitter part, 16 short preambles are being repeated 10 times to create a 160 length short preamble. So we'll use this property for perfect correlation. The period is 16, that is 16 short preamble slot time has been repeated 10 times, and the delay that we saw was of 8 samples. So we will use that. And now let's see how the correlation signal for packet detection has been constructed. So this is the signal that is being finally constructed. When we check the plot of the signal, we'll see we are getting a good enough signal to check the packet fronts. We have a packet front initially, and then we have two more packet fronts at 490, 976, and 1462. One more property that we need to see is the end of this packet front and the start of next packet front. The difference is more than 300 samples. So in that way, we can distinguish between other correlations might happen that they may come above the threshold of 0.75 that we will set. So in order to distinguish them from the perfect correlations, we'll set two properties. The first one will be the length over threshold. This length over threshold, we can see the first sample is at 492, the next sample is at 620. That means the length over threshold for this correlation, if we set it more than 100, then we know that this part is part of the packet front, and the distance between two peaks, if it is more than 300, then we know that one of the set of samples is part of the packet front. So we'll use this property. We'll set the length over threshold to be 100 and the distance between two packet fronts to be 300. And the next part that we need to set is this frame down sampling we are checking from RX signal. RX signal is the signal that was constructed from the signal that is oversampled by 8. So wherever packet front, this IDX is the index at which packet fronts exist, which is being assigned here. So wherever the packet front has been identified in the code, we will have to multiply it by 8 because the packet front was identified on the signal that we reconstructed similar to original signal, and that had length of 480 samples. But the signal that has been oversampled by 8 has length of 3888 samples. Hence, in frame down sampling, we'll need to multiply the packet front by 8 at both the locations. I think now we are good to go, and the MATLAB loopback should work. So the error that we have received is in line number 62, there is some error for matrix multiplication. So if I take the transpose of this, now the matrix multiplication should work. There is one more error because of which this is not running, which is when we have set the size initially, we set it along the first dimension, which is this dimension. In 31104 cross 1, this is the first dimension, and the next one is the second dimension. Right now, our DEM, the exact size in the second is in the second dimension. So I'll tell it to check the size along the second dimension. And now this code should work continuously. So this is how MATLAB loopback can be accomplished from the original code that we downloaded from GitHub. In the next part, I will integrate the tool in this code, and then we will run this code using antennas on RFSoC. Thank you.